Alright, in the last video I did not get too much into representative rectangles. Basically whenever your teacher draws one of these area or volume problems, what they're going to do is they're going to sort of, after sketching the two curves, they're going to sort of draw in a little rectangle like this. And that's just one of the infinity of rectangles that's put in, because basically when you do a Riemann sum, remember how in Riemann sums we'd basically take the area we want to estimate the area of and we'd break it into n equals 5 or n equals 2 or 5 or 6, 4 rectangles, whatever. So we'd sort of like take the region, break it up into 4 separate rectangles, and we knew it wasn't perfectly accurate, but basically to find the area of a weird shape, you can break it up into rectangles that sort of follow the contours of the region, add up the rectangles, and you'll get some estimate of the area. Well, then as we found when it moved into definite integrals, what's going on with an integral, we didn't have to talk about this at the time because it wasn't necessary, but with an integral, what an integral is sort of doing is automatically doing a Riemann sum only with like a lot of rectangles. Not 3 rectangles, not 10, not 100. It's basically infinity rectangles. So when you integrate to find the area between two curves, the integral is sort of automatically adding up the area of infinity little very, very skinny rectangles. Very, very skinny, right? They obviously have to be awfully skinny if infinity of them can fit between, as working across this region. Infinity rectangles crammed into a skinny area means extremely skinny rectangles. But that's what an integral is doing. So the reason the teacher is going to draw this representative rectangle, they're saying, you know what? There's infinity rectangles that are going to make up this region, but I'm just going to draw one of them to kind of show me what's going on. So if you draw this little rectangle, to find the area of a rectangle, you need the width and the height. The height is simply going to equal the y value minus x value. So that's where we get f of x. Oops. F of x is the top curve, and then g of x. So f of x minus g of x, that's literally just the y-coordinate of the top minus the y-coordinate of the bottom. And of course, if you take one y, subtract another y, you're going to get the difference between them. And that is the height. So when we integrated f minus g to find the area of a region, we're really just integrating the length of each one of these individual little rectangles as we move our way along the curve. Now what is the width? What's this width right here, this little w? We just said they're really, really skinny rectangles, right? To fit infinity of them into this region, they gotta be itty bitty little skinny guys, but how wide are they? That's actually what dx is. So you want to think of dx as the width of this little rectangle. I know that doesn't make a ton of physical sense, but it makes more sense than just say and take my word for it, okay? So trust me, if you start thinking about dx as the width of that little tiny rectangle, that's going to help you visualize what's going on, especially as you get into volume problems. So when we to find the area between two curves, when we integrated f of x minus g of x dx, what we're really saying is, hey, here's the height of the rectangle, here's the width, and of course height times width gives you area of the rectangle. And then by integrating from a to b, that's when we took infinity of these little rectangles and added them all up to get our area. So that's what's going on, but guess what? Notice how my width is dx right here? But if you've had this chapter in class at all, you realize there's also problems that have dy. So what's going on there? Well, it turns out, I say it turns out all the time, but here's the deal. It turns out that sometimes you don't want to use vertical representative rectangles. And some classes, depending on how hard your class is, will do Riemann sums in the y direction as well. It's hardly ever you see it, but when we did Riemann sums, and we always used vertical rectangles, so we'd like break the region up into 4 or 5 vertical rectangles. Instead, we could have broken them up into horizontal rectangles. Same difference, right? We could have broken them up into horizontal rectangles, and then we would have used a function in terms of y instead of x, it turns out. But the point is, if you want to add up an area, either estimate it with Riemann sums or find the exact area using a definite integral, you can use either vertical or horizontal little rectangles. It doesn't matter which one you do, except here's the trick. If you do a horizontal rectangle, we just switch things up, because now this little dimension, the width, is sort of a vertical dimension, right? The width, you can see this is sort of like parallel to the y-axis, the width is. So this is now dy. Instead of being a little piece of x direction, it's a little piece of y direction. It's a really, really skinny, but it's vertical. So now we got dy as the width. So what do you think that does to our integral formula? between two curves. Well, now instead of integrating from with dx, we got a dy, because now the width, I'm sorry, wrote dx, I'm so used to it. So now our width is dy. Interesting. What does that make h? We'll just call these a and b still. They're a different a and b than the other ones, but point is, we'll still have limits of integration, but now we're going to have f of y minus g of y. Because if you want to integrate in terms of dy, all the letters have to be y's. You may have noticed that whenever we integrate, the letters are always all the same. It's all either all x's or all thetas or all t's or whatever, but those letters have to match. So if you decide, and we're going to get into why you do this in a second, but if you decide that you want to do a dy problem, that means your two functions have to also be in terms of y. All right, so I feel like I've meandered long enough here. That's sort of the general theory of what's going on, and that's how you visualize it. If you're using horizontal little rectangles, you need to do a dy. If you're using vertical rectangles, you need to use a dx, and vice versa. So, and then the other big thing to take away from this is that if you are going to use dx's, you need functions in terms of x. If you're going to use dy's, you need to get your functions in terms of y. Turns out it's not that big a deal to get them in terms of y. It's just a little bit of algebra. Because I know you're thinking, hey, I've seen f of x's like for years now. I've never seen an f of y. Well, it turns out we just rearrange the equations. So this slide is no big deal. These equations are just like the ones we did for dx. We just, now because we have a dy, got a y there. And then of course when we turn these two integrals into one, just by, getting rid of some of the busy work, sure enough, we still got y's and dy's. Now the one little subtlety here is in the previous video when we're doing dx's, it was always the upper function minus the lower function. But of course when you got a sideways rectangle, up and down don't matter anymore, it's right to left. So one way of looking at it, it's now going to be the right one minus the left one. But like I said in the last video, if you get them backwards, all that happens is you get a negative answer, and just make it a positive and you'll be okay, and you'll have the right answer. So instead of being upper versus lower, it's now right versus left, but the same thing still applies. All right, so here we go. Let's do an example. Now what you'll notice right away here is that the functions are given, everything's in terms of y. In the previous video, it was like x equals 0, x equals 2 were the limits of integration. Now we've got y equals 0 and y equals 2. And right here we've got, instead of y equals a bunch of x's, we've got x equals a bunch of y's. And x equals y. So all this is sort of pointing you towards, hey, these are functions of y. I could replace this with f of y. Replace this x with g of y. And now I've got a couple of functions of y, right? So I can just subtract them. And as usual, we'll want to graph this thing. So our bounds are between 0 and 2. So our region goes from 0. Y equals 0 is a horizontal line at the x-axis. Y equals 2 is just a horizontal line up here. Now what does a graph of y squared plus 2 look like? It's a parabola, but it's a sideways parabola. So one thing that doesn't really come up usually in Algebra 2, but y squared plus 2 is just a parabola that's been knocked on its side. But other than that, it's just like a normal one, but we can always graph it by plugging in points. So if you want to know, if you plug in y equals 0, but of course, in a normal parabola, you'd plug in x's to get y, but this one's sort of set up with y as the independent variable. So we'll plug in y's to get x's out. So if we plug in 0 for y, we get 2 for x. So 0.02 is on there. If we plug in 1 for y, we get 3 for x. If we plug in 2 for y, we get 4 for x, or 6 rather. So it's going to basically shoot off up there. So I know that kind of went behind my picture real quick, but the point is we got a region here that goes from 0 to 2. The y coordinates go from 0 to 2, and then the right-hand curve is this y squared plus 2, and the left-hand curve is this negative y. Oh yeah, where's negative y? That is this line right here. It's just a line through the origin with a slope of -1. All right, so there's our region. It goes all the way over to that angled line. So this is x equals -y right here. And then this parabola is x equals y squared plus 2. So that means when I go to plug into my formula, I've got a dy, which means that my limits of integration are the y values. It's the range that y goes through because I have a y right here. So my limits of integration are 0 to 2. If we'd been integrating this same region in terms of x, we'd have a lot more ground to cover. We'd have to go from all the way over here in x to all the way over to the intersection of these two curves way off to the right, which happens, I think, at 6, at x equals 6. But since we're just looking at the y range of values because we're doing dy, that means we're just going from 0 to 2. So now I just drop in my usual deal, one function minus the other. So my rightmost function, my positive one, is y squared plus 2. Then I got to subtract my left one, which is negative y. So that is the integral from 0 to 2 of y squared, and then these negatives cancel to positive, so I got y squared plus y plus 2 dy. Alright, so now just because it's y's, still integrates the same. Integral of y squared is 1/3 y cubed. Integral of y is y squared over 2. So 1/2 y squared, and plus 2y, all from 0 to 2. I'm going to plug in 2. 2 cubed is 8, times 1/3 is 8/3. Y squared, so that's 2 squared is 4, times 1/2 is only 2. And 2 times 2 is 4. And then I need to subtract, so that was all when I plugged in my upper limit. Now I got to plug in my lower limit of 0, but that's just going to be 0, 0, 0. So that goes away. Alright, so you end up with 2 and 4 is 6. So that's going to be 18/3. Yeah, 3 times 6 is 18. Plus 8/3 gives us 26/3. Alright, for whatever reason, they look messy, but I don't tend to make any algebraic errors on these the way I do with the limits and improper integrals if you've already watched that video. So here's hoping. Honestly, students do pretty well with this. It's the setup of the problem that's super hard, getting the sketch right, and then setting up the initial equation. But usually they're polynomials at that point. Usually the integration itself is very easy. There's no u substitution to worry about usually. So where these get nasty is in the initial setup. But if you just realize, hey, I'm dealing with functions of y, like both these functions were in terms of y. So I'm just going to do a dy problem. Drop in a dy, figure out the limits of integration based on y, because as soon as you're using dy, you got to use the y as your limits of integration. And there you go. All right, rearranging for f of y. So if you look at this one, we got an area where everything's bounded. But you'll notice there's a little bit of confusion going on here. These functions are given in terms of x, so these kind of look like functions of x. And yet I'm given limits of integration in terms of y. So y is going from 0 to 4. But what I can do, first let's graph these, but then we can integrate by converting these to functions of y. So first of all, let's look at what these look like. We got y equals negative x again. It's supposed to be a straight line. So that's y equals negative x, and then x minus 1 squared. That's a regular parabola, but it's shifted to the right one. It's the opposite of that one, so it's to the right. So this goes like this. Crosses at 0, 1, and takes off like that. And then y equals 0 is right here. It's a horizontal line. And then y equals 4 is up here. So it looks like they want us to find this whole region in here. All right, I'm going to unsketch that for a second just because I want to be able to draw my representative rectangle. So if you look what's going on, this is an example of when we want to work in terms of y. And in the next video, I'm going to get into more hard ones like this, but the point is that if you were to draw your representative rectangle like this, for this whole left-hand region, the top curve is going to be that horizontal line, the bottom curve is going to be the diagonal line. So that's very simple. But then once we cross this point of intersection, then our representative rectangle is going to have a top curve that's this parabola thing, and the bottom curve is going to be the angle, and then it's going to switch again when we get down to here. So we'll have to break this up into 3 separate integrals if we tried to work this in terms of x. But if we're working in terms of y and just use horizontal rectangles, then we just need one integral, because the whole time I'm going from up here, if I integrate from 0 to 4 in y, the whole time I'm working my way up this region, my little rectangles always have one end on that parabola and one end on the line y equals x. So that's why we want to work this one in terms of y. But the problem is, of course, I have functions in terms of x. So what I have to do is sort of solve these two equations for x in order to get them in terms of y. So start with this first one, y equals x minus 1 squared. First thing to do is square root both sides. So now I've got plus or minus square root of y equals x minus 1. To get x by itself, I've got to add 1 to both sides. So I get 1 plus or minus square root of y equals x. So that is the parabola thing. And then the other one's a lot easier. If y equals negative x, that means that x equals negative y. So my two curves are x equals negative y, and then this thing right here, which is 1 plus or minus root y. Now why is there a plus or minus? It's because I square rooted a variable, and just like with when you're completing the square or something, when you take the square root of a random letter, you got to put a plus or minus out front. What's really going on there, though, is that the plus in front of the square root represents the right-hand side of this parabola, and the negative root represents this side. So I'm actually going to need to use the negative one, so that means that x equals 1 minus the square root of y. And if you plug in a few points real quick, you'll see that that's true. So we plug in 0 for y, we still get x equals 1. But if we plug in 1 for y, we want to get x equals 0 to get this point, and sure enough, that is. So this is the equation that's going to follow that left-hand side of the parabola. All right, so now I got my two functions. I got this, and I got this. So I can integrate. Y is going from 0 to 4. I already know that. So integral from 0 to 4. The right-hand curve is the 1 minus root y. Now I got to subtract the left-hand curve, which is negative y. All right, so those cancel to positive. So I get, looks like I'll just rewrite this though as a fractional exponent. 1 minus y to the 1/2 plus y dy. All right, so now we're ready to integrate. This is not a good problem. So we get y minus y to the 1/2 becomes y to the 3/2. Divided by 3/2 gives you 2/3. Hopefully you guys are pretty solid at the power rule at this point. Plus 1/2 y squared, all integrated from 0 to 4. So that's going to give us, when we plug in 0, we're just going to get nothing. So we just have to plug in the upper limit, which is 4. So we get 4 minus 2/3. What is 4 to the 3/2? The trick is you take the square root of it first, so do the half power first to give you 2, and then cube it. So that gives you 8. Plus 1/2 times 16, which is 8. All right, so 4 plus 8 is 12. I'm going to subtract 16/3. So 12 is 36/3. Minus 16/3 equals 20/3. Tasty stuff. Hopefully that's right. Those fractions got a little wacky there for a second. All right, so hopefully what we saw there was that you don't really need to fully follow why we had to do dy on that problem, but the main point was that if you draw in a bunch of representative rectangles that are all sideways, the right-hand end of each rectangle was always on the parabola, and the left-hand end was always on x equals negative y, on this diagonal line. If you did the vertical rectangles and drew in a bunch of them, sometimes they had one end on a horizontal line, sometimes they had one end on a parabola, sometimes they had one end on a different horizontal line, so that's why it was all messy and we had to do dy. All right, once again, our classic area between x cubed and x squared, but this time we're going to work it in terms of dy. So as we learned in our last video, x squared is going to be like this, and then x cubed is actually going to go underneath it, kind of be creating a sliver crescent shape here that crosses at 1, 1. So this is, and as we, x squared is actually the one above, and x cubed is on the right here. But of course, we don't want x squared and x cubed because we're going to work this in terms of dy. So what we need to do is switch these to whatever they'd be as functions of y. So if y equals x squared, then you square root both sides and you get x equals square root of y. It's actually plus or minus square root of y to get the 2 halves of the parabola, except we know we want the positive half. We want the one on the right here. So that's why we get x equals positive square root of y. And then x cubed, same story, y equals x cubed, which means that x equals y to the 1/3, or the cube root of y. And since this was a cubic, we don't have to worry about that plus or minus thing. So here's our 2 functions. We just go ahead and integrate. So we need the integral. Now what range of y are we going to follow? Y is going to go from 0 to 1. There's actually the same limits we had when we did the same problem in x in the last video. So we've got the right-hand curve, which is y to the 1/3. So we got y to the 1/3 minus y to the 1/2 dy. And the fact this is y is what tells you this has to be the limits of integration of y, not x, over the region. So y is going from 0 to 1 through this region. And of course, if we drew in our little representative rectangles, it'd all be sideways little guys. So let's integrate. Y to the 1/3 integrates to y to the 4/3 times 3/4, because if you divide by 4/3, you end up multiplying by 3/4. And then minus y to the 1/2 becomes y to the 3/2. Of course, dividing by 3/2 gives you 2/3. So plug in, this is from 0 to 1. If you plug in 1, you just get the coefficient, so 3/4 minus 2/3. So that's going to be 9/12 minus 8/12 gives you 1/12. Hopefully I didn't go too fast on those last few fractions, but the point is 1/12, which you may recall is the exact same area we got working this in terms of x. So the method works. We just worked this on the previous video. We worked the same problem using the functions in terms of x and then integrating in terms of dx. So we had a dx right here instead of a dy. And we did from 0 to 1 still, because that's also the range of x. This region covers from 0 to 1 in x and also 0 to 1 in y. But the point is we got 1/12 twice. So that is pretty awesome. The magic works. All right, intersecting curves. Same story as with when we did the dx problems. You know, they could either give you an interval or they could just say, hey, wherever they intersect. So we've got x equals y squared again. I say again, I'm not sure we've done that one yet. It's just a sideways parabola at the origin. So y equals x squared is just your classic at the origin vertical parabola. X equals y squared is just your classic sideways parabola. I mean, it's like the simplest sort of parent function of the sideways parabola. And just to show you that you've actually seen this before, one of the parent functions in precalculus is y equals square root of x. But isn't that just this top curve right here? So just because in precalculus and algebra and calculus really, you're always working with the functions, right? The sideways parabola is not a function. So x equals y squared is not a function, but y equals root x is. Of course, if you actually square root this, you'll get y equals plus or minus root x, positive root x for the top half, negative root x for the bottom half. But let's see what happens. And then, of course, here's our line x equals 4. All right, so if we wanted to work this in terms of x, so dx, we would simply go, our top curve would be positive root x, and our bottom curve would be negative root x, so it'd be integrating from x equals 0 to x equals 4, top curve, square root of x, and I subtract the bottom curve, which is negative root x, so those negatives cancel, and of course that's times dx. So, and you can work this on your own right now if you want. You could integrate from 0 to 4, 2 root x dx, and you should get the same answer as what we're about to get. So I would say this is not an ideal region because like the dx was a little bit confusing. If you weren't, as experienced as I am, or even you might not realize that, oh, the upper span's positive root x, the lower span's negative root x. That's a lot of stuff to keep track of, right? You'd have to be really clever and remember that whole thing about positive root x's and negative root x's. Otherwise, you'd accidentally only get this portion of the area, not the whole area. But of course, because we need to get this whole thing, so our vertical bars, our dx bars, would have gone from negative root x all the way to positive root x. Those are our represented rectangles. It turns out that working it sideways with dy's is actually better, because then all our rectangles just go from that line x equals 4 to the parabola x equals y squared. These are just a couple of representative rectangles, but of course, after we're done integrating, we will have had infinity of these little rectangles. But each of these lines I just drew, you can see that they begin on the parabola and they end on the vertical line. So let's try integrating this in dy. Our range of y is not from 0 to 4. Our y's go from, I believe this is 4 comma negative 2. And this point right here is 4 comma positive 2. So the range of y values that we're going to cover that are sort of encapsulate this region, we go from a low point of negative 2 to a high point of positive 2. So we're going from negative 2 to 2. And then our right-hand curve, so we're doing the right curve minus the left curve. The right curve is just 4, x equals 4. And then this left-hand curve is just x squared, y squared. So we got 4 minus y squared. All right, so now we just integrate. So it looks ready to integrate to me, so let's just integrate it. 4y minus 1/3 y cubed from negative 2 to 2. So let's plug in our top limit integration. 4 times 2 is 8, minus 8/3. Now we got to plug in negative 2. So we get 4 times negative 2 is negative 8. And then negative 2 cubed is negative 8 times negative 1/3 is positive 8/3. But of course, when you distribute this negative sign, that turns positive, that turns negative. So now I've got 8 plus 8 is 16. And then minus 16/3. So that's 48/3 minus 16/3, which gives us 32/3. Pretty rad. Now, if you worked this, you should have gotten that exact same answer. And I encourage you to do that now just to see that it actually works out. So we've sort of demonstrated with that x squared x cubed classic example, and also with this one, that if whether you're working with dx or dy, you should get the right answer if you do it right. It just depends on the region, what shape the curves are, what the equations of those curves are. It just depends which one is easier, x or y. On this one, we obviously said, came in with, we're in the dy video, so I said, hey, let's work it with dy. You could have worked it with dx as well. And that's going to be true a lot of the time, but usually one will be easier than the other for a given region. So in the next video, that's what we're going to take a look at. If you're not in an AP class or sort of a science and engineering calculus class, if you're just in sort of one of the economics or business calculus classes, you might not need the next video. I would still encourage you to watch it, because even if your problems don't get quite that hard, it'll probably clear up a lot of the confusion about why all this is going on in the first place. And it's also really going to help you in the revolved solids or the volume section that's coming up after this, because that is, like I said, the hardest chapter in calculus, and it's the one that students have the most trouble with, and that's one I get most calls about, and the longest sessions and the most panic all come from that volume chapter. And the sort of way of thinking we're going to establish in the next video is really going to go a long way towards clearing up the confusion about the volumes chapter coming up next.